Hello, you're welcome back. All right. Okay, so here we're going to continue from where we stop. Uh, well, now we're going to be looking at different effects of electrical current. Right, electrical current can produce the following effect. Electrical current can produce heat effects. Okay, and of course you actually find this in electrical heaters. Why where you when you plug an electrical heater into an electrical power source, okay, it actually heats up, it produces heat. Now we've already talked about this when we treated determination of specific heat capacity. Now chemical effect. Now electrical current can actually create a chemical reaction, okay, that is in electrolysis. If you want to charge battery, okay, you actually apply direct current to that particular battery, and that direct current is going to create electrical reaction, okay, which of course is a process of charging a battery. So in this tutorial we are going to talk about the magnetic effect. For this other two effects, okay, they are different topics, okay, it has been treated in a different topic, right? So we'll talk about magnetic effect of electric current. Now, what is magnetic effect, okay, of electric current? Now, anytime uh, there's a current carrying conductor, or anytime a conductor actually carries current, okay, let me just let's say I have a wire, all right, that carries current. Now it has been noticed that this wire has magnetic field around it, okay, so there's magnetic field around this particular wire, which of course it can be drawn, right, in form of concentric circle that has direction. Now the question is, how do I actually get the direction of the magnetic field? Now the direction of the magnetic field in a current carrying conductor depend on the direction of the current, right? And there are rules, laws that can help us determine the direction of the magnetic field. So these are the laws we are going to be looking at. Now the very first law, okay, that will help us get to know the direction of the magnetic field with respect to the direction of the current is known as the right hand clench rule. Okay, the right hand clench rule says that if a wire conductor is being clenched by the right hand, okay, with the thumb pointing in the direction of the current, then the magnetic field will be pointing in the direction of the other four fingers, as you can see here. Okay, so thumb is going up, then the magnetic field is actually going counterclockwise. This is anti-clockwise, okay. So invariably now, if the current is actually, if you turn this, all right, the current is downward, then the magnetic field would now go on a clockwise direction, all right. Now this is one method of determining the direction of magnetic field with respect to the direction of the current. There's another rule, okay, which of course we go that help us to determine that is corkscrew rule, Maxwell corkscrew rule. Okay, this one states that if the direction of the corkscrew represent the direction of the current. Now a corkscrew is just like your normal screwdriver that you actually drive into a nut, okay, or into any particular body, right? By remember, if you want to actually drive a screw, you use a screwdriver, and if you want to drive it into a particular let's say into a chamber, okay, you have to rotate the screw in a clockwise direction. So this rule is trying to say that the direction of the screw, if the direction of the screw, okay, is represent the direction of the current, then the direction of the rotation of the screw becomes the direction of the magnetic field. So I think a diagram actually illustrates that. Let's look at this. Okay, so let's say this is actually a screw that can be driven by a screwdriver. So if I turn the screw, okay, clockwise, then the current actually goes down, right? So for downward movement of the current, okay, then it simply means that I have to turn this clockwise. So the turning of this, the clockwise movement of this, becomes the direction of the magnetic field. So if the magnetic field is downward, then the if the current is downward, please pardon me, the magnetic field will be in a clockwise direction. But if the current is upward, then the magnetic field will be in anti-clockwise direction. So I hope that is well understood. Okay, so I think that is it. Now we are going to look at the application of the magnetic effect of electric current application. Okay, now where do we find the magnetic effect of electric current very useful? Now, magnetic effect of electric current is used in instrumentation. Okay, so in the area of instrumentation, we find the magnetic effect of electric current very useful. Now, what is instrumentation? Instrumentation is the principle of operation used in the construction of electrical measuring instrument. Okay, so the instrument that is used in electrical measurement, okay, is being their construction, their principle, the principle behind their construction is known as instrumentation. Okay, so now basically the electrical measuring instruments that we have in the laboratory, okay, there are just three major electrical measuring instruments. We have the galvanometer, we have the ammeter, and the voltmeter. The galvanometer is simply a device that is used to detect the presence of current. It can only measure, okay, detect presence of current. That simply means it can only measure very small amount of current. Okay, it doesn't measure a reasonable amount of current. But for an ammeter is a device that is used in measuring current. Okay, we now have the voltmeter, that is a device used in measuring, okay, an instrument that using measuring voltage. Okay, now how is all this constructed? Now both the ammeter and voltmeter is being constructed from a galvanometer. So galvanometer is actually the foundation for the construction, okay, or the instrument that is used to produce ammeter and voltmeter. Now let's look at galvanometer. Right now, what is a galvanometer? It's a device that is used to measure very small amount of current. Now it utilizes torque. Okay, it utilizes torque produced in a current carrying coil placed in a magnetic field. Anytime a coil of wire is carrying current, and that can, remember, a coil of wire carrying current has magnetic field inside it. Now you are bringing that coil of wire to, you're bringing it in between external magnetic field. Okay, due to an interaction of the magnetic field of the coil and that of the external magnetic field, there's bound to be a torque, a kind of torque, the turning effect. All right, so this torque causes the pointer of the galvanometer to deflect along the scale in proportion to the quantity of current it receives. So due to that, then the pointer deflects. Okay, and that deflection of the pointer depends on the current. So that way we can simply say that a galvanometer, all right, always deflect, okay, anytime current is being supplied to the coil, right? And it now can be used to measure small amount of current. Now the diagram of a galvanometer is shown. Now let's look at the diagram. Let's look at what you're talking about here. So as you can see, there is a coil. This is actually a coil. All right, okay, about that's actually one around a cylinder. A coil went around a cylinder, a cylinder of soft iron core. Now in between the coil, in between the coil lies external magnetic field north south, all right, at either side. So now this coil now has terminal to which I can actually connect to an external current. So once current flows through the coil, there's going to be a kind of a torque will be produced due to the interaction of the external magnetic field and the internal magnetic field of the coil due to the current. So that will cause the pointer to deflect in the scale, to deflect according to the current it receives. All right, so this is a galvanometer. So as you can see, this is the principle behind every measuring instrument. That is how. So both the voltmeter and galvanometer have this construction. That is why I say that voltmeter and galvanometer is constructed from voltmeter and ammeter, pardon me, is constructed from a galvanometer. All right, so but before you can actually convert a galvanometer to an ammeter or voltmeter, there is something that you ought to actually apply. That's something you need to introduce, and that is what you're going to be looking at. Okay, now we will talk about that. All right, this is not what this is different. Okay, all right, so let's talk about that. Okay. I will now talk about the conversion. Let's see how we can convert, okay, a galvanometer to ammeter. All right, now of course the electrical symbol of a galvanometer is this the electrical symbol of a galvanometer. So I need to actually convert this galvanometer to an ammeter, which simply means that I need to actually use this galvanometer to measure the current that an ammeter will measure, right? So I need to use it to measure the current. So let's say this is the current, all right, IA, that an ammeter is supposed to measure. Then I want this galvanometer to measure it. Now, by default, a galvanometer can measure this amount of current. Okay, why? Because it's not actually constructed to measure high current. Okay, it's only constructed to measure very small micro current. Okay, so for me to be able to measure this current IA by the galvanometer, I will have to, because if I allow this entire current to pass through the galvanometer, it will burn the coil. So I have to divert some of this current. Okay, then I have to create a diversion. All right, I have to create a diversion. So this is what we have. Now I will now have to divert it so that I divert it now so that excess current, okay, that would have actually burned this galvanometer will now be introduced to a resistor that is known as a shunt resistor. All right, a resistor known as shunt resistor. So shunt resistor, I call it RX. So which simply means that if you are being asked how do you convert excuse me, please pardon me, how do you convert an ammeter, okay, a galvanometer into an ammeter, okay, I will do that by connecting a resistor, okay, known as shunt, in parallel with the galvanometer. What is the function of the shunt? The shunt is to divert the excess current, okay, that would have entered galvanometer divert it into this shunt, right? So now let's look at how. So the question is, okay, what is the value of this shunt that is needed? That's always the question. So in exams, you need to find this value, the resistance of this shunt, okay, that is needed for this conversion. How do I get this? All right, so as I said, let IA, or better still, let me just use I, okay, be the current that I want to measure, okay, let it be current. So if that current reaches here, okay, the galvanometer can only take the current, the maximum current I can take, okay, we call it the full scale deflection, the current that gives the galvanometer full scale deflection. I use IG to represent that. Then the excess now, okay, and of course, how do I get the excess? the total current is I. The maximum, the one that's entering galvanometer is G. So the excess that will now enter into the shunt resistor is going to be equal to I minus Ig. Okay, so that is the current that's entering into the shunt. All right, now don't forget that the galvanometer will still have its internal resistance, okay, Rg. So now both the shunt resistor and the galvanometer, they are in parallel, okay, and you know very well that if if devices are parallel, all right, or resistors are in parallel, the voltage, okay, in a parallel connection is always equal. So I'll simply say that, all right, the voltage across the galvanometer G, all right, is still gonna be the same voltage across the shunt because they're in parallel. So now, according to Ohm's law, voltage is current times resistance. So the voltage across galvanometer is gonna be the full-scale deflection, Ig, the current of the galvanometer multiplied by Rg, okay? Resistance of the galvanometer. The full scale, Ig is the full scale deflection of the galvanometer multiplied by the resistance of the galvanometer. Then for the shunt, okay, the current of the shunt, of course, here is I, all right, minus Ig in bracket, then multiplied by the shunt resistor, and that's what we're looking for. So from this relationship now, I can simply conclude that, okay, for me to get the shunt resistance, all right, that is needed for this conversion, that's gonna be Ig Rg, all right, then divided by I minus Ig. So this is a formula in case you see this in exam. Okay, so let's write down these parameters. The Ig, okay, is what is always known as the maximum current of the galvanometer. Okay, they call it full scale deflection current. Is the maximum current that the galvanometer can actually take. Right, and of course, you know, Rg is the resistance of the galvanometer and other parameters there. So take note of this formula, right? That is how you convert a galvanometer into an ammeter. Now what? Let's look at the other conversion, okay? Converting a galvanometer. Please, galvanometer is stated as milliammeter, okay? Galvanometer. Okay, because it measures its current in milliampere, very small ampere. Okay, our galvanometer to voltmeter. Okay, this is how this one work. Remember, what it has to do with voltage, all right? Voltage is always across. So I want to measure voltage. Let's say V. I want to convert this V, okay, by a galvanometer. Then definitely that simply means that I need this galvanometer, all right, to actually measure voltage. But if I should connect the voltage V, all right, of the voltmeter into a galvanometer, it will burn it is too high for the galvanometer. It will burn it, all right. So for me to actually achieve this, I need to divide the voltage. All right, remember voltage is, if I want to divide voltage, I add series. So what I would do in the case, let's say this is a galvanometer, right? Okay, so for me to divide the voltage of the voltmeter, I'm going to actually connect a resistor, but this time around in series. Okay, so that resistor is what is known as multiplier. All right, so that this voltage, this is the galvanometer, right? So the voltage I want to measure, V, all right, would definitely, all right, will not be connected across the galvanometer alone, but rather will be shared, okay, between the galvanometer, that is VG, and of course the multiplier that is connected in series, VM. Now don't forget that the galvanometer will still take its maximum current, which is IG, full scale deflection. But it happened that since the galvanometer and the multiplier are in series, so the same current passing through the galvanometer is what will pass through the multiplier. All right. So now let's apply the voltage. Okay, the voltage supplied is equal to the voltage that go across the galvanometer plus the voltage across the multiplier. All right, so the voltage I want to measure V is going to be equal to voltage of the galvanometer, of course, is given as IG. That's the resistance of the galvanometer, right? Then voltage of the multiplier is going to be equal to the same IG. IG is the same current passing through the multiplier, then times the resistance of the multiplier. Now, the whole idea is for me to get this resistance of the multiplier. So I have to rearrange this equation. So I'm having IG, all right, Rm being equal to V, right? Then minus IGRG. Okay, so the multiplier resistance now that I need to achieve this conversion is gotten by this formula. V, okay, minus IGRG, then divided by IG. So this is the formula we use to, we need to find the multiplier that is used to convert a galvanometer into a voltmeter. So please take note of that. Take note of this. Then of course take note of this. Okay. I think if there's an example, I would have actually applied that. But let's proceed with. Okay. So basically that is it. So let's look at an application. Then I will solve questions. Okay, let's look at that. Let's say you have a milliammeter. Okay, milliammeter. Anytime you hear of milliammeter, okay, it's not as galvanometer. Now a milliammeter, okay, whose full scale deflection is let's say 2 milliampere. Okay, and of course it is needed to measure a current where it's needed to measure a current, okay, as large as 2 ampere. So now the question is, what is the value of the shunt resistor that is needed for this to happen? Okay, if the resistance of the galvanometer is let's say 20 ohm. So that now brings us to the formula. Don't forget the formula. Okay, shunt resistor is given as Ig. Please write it down somewhere. Ig RG, then divided by the current I minus Ig, the full scale deflection. All right, so we could do this. Ig is 2 milliampere. You have to convert this to ampere. Converting milliampere to ampere, you divide by 1000. So that's going to be 0.002, right? Then times the resistance, which is 20, then divided by the current that I want to measure 2, then minus the full scale deflection 0.002. Okay, so I think with this, just use calculator solve this, okay, to the end, and that will give you Rx. So I hope that is well understood. Now there are questions which, of course, is a continuation, okay, of current electricity that I need to solve. I think I have to still do justice to them. I've solved this. I've not solved this question. Let's see. I stopped somewhere. I want to solve questions here now. Okay. Okay. So let's solve questions. We're gonna solve questions on the current electricity. So here we have. So this one goes like this: a cell can supply a current of 0.4 ampere and 0.2 ampere through a 4 ohm and 10 ohm resistor respectively. The internal resistance of the cell is, okay, so this cell can supply both 0.4 and 0.2 through, okay, 4 ohm and 10 ohm. So we're looking for the internal resistance. How do we do that? Okay, remember the formula for current. Okay, is E all over capital letter R plus small letter r. So we are told that from the question, this cell can supply 0.4 ampere, all right, to an external resistor of 4 ohms. So that means 0.4 ampere, all right, is equal to E, which wasn't given to us, the EMF of this cell. Then the external resistance of what's the external resistance of 4 ohms, right? Then plus the internal resistance, that's what we're looking for. Okay, that's what we are being calculated. So this is equation 1. Now the same cells now still supplies 0.2 ampere to an external resistance of 10 ohm. So this time around the current is 0.2 ampere. Of course, it's still the same cell, so it has the same EMF. Okay, to an external resistance of 10 ohm plus the same internal resistance. So this is equation 2. So we now discover that if I should cross multiply, okay, from equation 1, right? If I cross multiply equation 1, I have that E is equal to 0.4 open bracket 4 plus R, okay? Then if I do that, let me call this now, okay? I just made E the subject, okay? If I do that from equation 2, if I still cross multiply, then the E, okay, E now is 0.2 times 10 plus R, right? So E is equal to E, so I can equate this. This is equal to this, okay? So I can simply now have 0.4 open bracket 4 plus R is equal to 0.2 open bracket 10 plus R. Okay, so remember what you're looking for is R, the internal resistance. So I can open this bracket, right? So this should give us 4 times 0.4 should give me 1.6, right? Then plus 0.4 multiplied by R is 0.4 R. 0.2 times 10, that is 2. All right. Okay, hope I'm not mistaken. Okay. Then of course here I have 0.2 R. So collecting like terms, now I'm gonna have 0.4 R, all right, minus 0.2 R, okay, is equal to 2 minus 1.6. So when you subtract this, I'm gonna have 0.2 R, right, is equal to 2 minus 1.6 should give me 0.4. Okay, so R now is gonna be equal to 0.4 divided by 0.2. So that is 2 ohm. So the internal resistance is 2 ohm. I hope that is well understood. Okay, let's proceed. More question. Okay, so here I have another question here. It goes that this is a diagram, okay? In the diagram above, the ammeter reads a current of 3 ampere when R is 5 ohm. So when this R is 5 ohm, ammeter, the current, okay, that's entering into these two resistors is 3 ampere, right? Now when this R is 5 ohms, then the ammeter current is 6 ampere. So now let's go again. Diameter is 3 ampere when R is 5 ohm, okay, and 6 ampere when R is 2 ohms. So determine the value of X. So there's no internal resistance. So this time around, it's still the same formula I'm going to apply here, okay? Of course, I is equal to E, right? Divided by capital letter R plus small letter r, okay? So now, according to the question, we'll have a reading of 3 ampere for when R, capital letter R. Okay, now capital letter R, you should take note of, okay, there's no internal resistance. I only have 2 external resistance connected in parallel. So the total resistance, okay, for that connection is going to be, remember, product all over sum, okay? That's R x divided by R plus x. So this is the total, okay, R. And of course, the internal resistance, there's no internal resistance, is 0. So putting that here now, I can simply have the, okay, I is equal to E, right? Then divided by Rx all over R plus X, okay? Of course, if you should invert this fraction, okay, what you have, this now comes up E multiplied by R, okay, R plus X divided by, okay, is it really necessary for me to do that? Okay, no, it's not necessary, okay? I can just keep it this way, okay, so that I can. All right, so now having done this, now let's go to the question. So when I is 3 ampere, right, capital letter R is 5 ohm. So let's establish that, okay? Let's establish that when I is 3 ampere, I have E, okay? R at that point is 5 ohm. That is going to be 5x, okay, divided by, okay, 5 plus x, okay? So if I should cross multiply, right, E is going to be equal to 3 times, okay, 3 times 5, which of course is 15. If I cross multiply, I'm going to have 3 times 5x, that's 15x, all over 5 plus x, okay? Then I'll do the same for the other. Let me divide this, okay? Now, according to the same question, now when the current is 6 ampere, then the R is 2 ohm, okay? So here I'm having 6 equal to E divided by Rx, 2x, right? All over 2 plus x. Cross multiplying now, the same E is gonna be equal to 6 times 2, that's 12x. So I'm having 12x divided by 2 plus x. Okay, of course, E is equal to E, so I can equate. So I will have 15x all over 5 plus x is equal to 12x all over 2 plus x. Okay, to make my simplification easy, okay, this product I can easily cancel x at this numerator. Why? Because it's just it's two factors, okay, which one is x, and it's find both sides of the equation, it will cancel out. Okay, that's a mathematical approach that makes this solution easier, but you can still cross multiply without canceling it out. All right, any method that will help you is not bad. Okay, any method you want to choose. So now I can now cross multiply, or having cancelled the x at the numerator. Okay, cross multiplying, I'm gonna have, okay, 15 multiplied by 2 plus x, all right, equal to 12 multiplied by 5 plus x. All right, open this bracket. 15 times 2, that's 30, plus 15x plus 15x is equal to 60. 12 times 5 is 60, then plus 12x. All right, so collecting like terms together, so I'm gonna have 15 minus 12, right, that should be 3x. Then 60 minus 30, okay, excuse me. All right, okay, so here we go. 60 minus 30 is 30, so my x now becomes 30 all over 3, which is, so the resistor x is 10 ohm. Okay, so I hope that is well understood. Okay, can go through it again. Next question. This one goes like this. A bread toaster uses a current of 4 ampere plugged in a 240-volt line. It takes 1 minute to toast slice of bread. What is the energy consumed by the toaster? All right, so this time around, the energy, we are just asked to calculate energy, not the power, the energy unit, okay, like the one we actually calculated in kilowatt hours. So this was just in joule, right? So if we are actually looking at this in joule, okay, the energy in joule E, all we need is to apply power times time, or okay, and of course it should be in their standard SI unit. Okay, so I have in this case I was given current and voltage. I will apply the formula. Energy, remember, power is, okay, current times voltage, then of course multiply by time. So let's evaluate. Okay, so now a bread toaster uses 4 ampere, the current is 4, the voltage is 240 volts, and that, okay, takes 1 minute. 4 times 240 volts, which took 1 minute. I have to convert to seconds by multiplying by 60. All right, so I hope this is 8, okay, 16. Okay, let's do that with, excuse me, with calculator of 4 times 240, okay, times 60. All right, 57600. watt. All right. Next question. A resistance R is connected across the terminal of electric cell of internal resistance 2 ohm. Okay, so this is another question. All right. Internal resistance is 2 ohm. All right, so let's go there. Okay, a resistance R. Okay, the standard resistance R is connected across um, a, a terminal of electric cell of internal resistance 2 ohm, right? And the voltage was reduced to 3 all over 5 of its nominal voltage. So by connecting this, all right, by connecting this the EMF, right, that has this resistance, the voltage that was supplied, okay, the voltage that was supplied reduced to 3 all over 5, okay, of each nominal voltage. So the question is the value of R is, okay, now don't forget the formula. E is equal to, okay, this time around, remember, okay, we have our I big R plus I small r. Okay, so now this terminal voltage, okay, this is the terminal voltage, I big R, okay, of course it's going to be equal to E minus I small r. Okay, so now let's see what happened. Okay, so according to the question, by, okay, this particular voltage, okay, was reduced to 3 all over 5 is terminal voltage, right? Now that means the voltage that was gotten as a terminal voltage was 3 all over 5, okay, the voltage it was supposed to have, that is 3 all over 5 of E, then E minus, okay, what do we have? Okay, the current was the current given, okay, now 3 all over 5 of E, so now have the current, the internal resistance was given as 2 ohm, okay, so I'm gonna have 2 I. Okay, so now to do this now, okay, I can actually rearrange this equation. So I'm gonna have 2I, okay, being equal to E minus 3 all over 5, 3 all over 5E. Okay, so 2I is gonna be equal to LCM is 5. So having 5E minus 3E. 2R is gonna be equal to, okay, 2E all over 5. Okay, of course, 2 goes, I'm having now the current is E all over 5. Okay, now let's see so the value of the big R now is what we are looking for. Okay, now don't forget that I is given as E all over R plus small r is equal to E, so all over 5. E cancels E, alright? So we're looking for big R, right? So this is going to be equal to 1 all over big R plus the small r, which of course has been given to be 2 ohm, right? So 2 equal to 1 all over 5. So it is not easy. I can just find the reciprocal or cross multiply. So if I cross multiply, I'm going to have R plus 2 is equal to 5. So the big R now becomes 5 minus 2, which is 3. Okay, so though tactical, but still flows with the same formula. Okay, so that is just that. Okay, we actually encourage you to go through this, possibly get more questions and solve. Okay, all right, so we're going to be looking at another topic. That will be the next video. All right, see you in the next video. Thank you very much.